All right, so we're on to nodal analysis. It's the first of the several methods we're going to discuss for solving DC circuits in this module. And let's just get right into the general process for using nodal analysis to solve a problem. It'd probably be best for me to just throw a little example circuit down here. So I'm going to go ahead and do that, and then we'll go ahead and go through the steps one at a time and determine what each of those steps means in the context of solving a circuit. Okay, so let's go ahead and say that I've got this circuit down here. You know what, I'll give myself some values as well. Just say 1 volt, 2 volts, 1K, 3K, and 5K. How about that? Okay, so the first step, it says we need to determine how many or which nodes in the circuit have unknown voltages. Okay, so before that, let's just go back to our little analysis of nodes in the circuit in general, and let's just go ahead and label them. So I've got one node here, I've got another node here, I've got a node here, and then lastly got my ground node here. Okay, so which of the nodes in this circuit have unknown voltages? Well, clearly ground is a known voltage, that's 0. And if I know that my voltage sources have ground at the minus terminal, then I know that the plus terminal is just equal to the voltage at the, the rating for that source. And so I'm left with just one node that has an unknown voltage, and that's this middle node. So let's give it a name. Let's call it Vx. And I'm done with step 1. Okay? So basically the problem here would be, let's solve for the node voltages in the circuit, or solve for the unknown voltages in the circuit. And so we know this voltage, we know this voltage, we know ground, of course, and so we're really just left trying to find Vx. Okay? And so step 2 says label all the currents into and out of each node from 1. Okay, so from part 1, we only came up with one node that had an unknown voltage, and so we're going to just go ahead and write or label all the currents into or out of each node. Well, in this case, it's just the one node. Okay, so let's do that. So I have a current coming in. That's the current through the 1K. We'll call that I1. It doesn't need to be coming in. I can label it going out if I wanted to. I could label them all going out if I wanted to. Or I could label them all going in if I wanted to. I could do either one of these, and what the math is going to work out such that, let's say later sometime I solve for I2 and I get something like I2 is equal to negative 1 milliamp. Well, what does that tell me? That basically just tells me that I really have 1 milliamp flowing in the opposite direction of how I originally defined it, okay? So if I define, let me just make this point again. I made this point before, but let me make this point again. If I define my current flowing from right to left like I have defined here, and then I solve for that current later in my circuit, I get that value is negative, then that means that the current is actually 1 milliamp in the other direction, right? So there's nothing wrong with defining them left or right or up or down. It really doesn't make a difference how we define our currents. If you think you know how the current's going to flow, that's great. But if you get a negative answer, there's nothing wrong with that. It just tells you that your initial guess on which direction the current was flowing was incorrect. It does nothing for the problem. You get a negative answer. You could go back and flip the arrow if you really want to, but the math will all work out. Okay, so let's call this I1, we'll call this I2, and we'll call this one I3. And so label all the currents into and out of each node. So we did that, the node that we're interested in from part 1. Okay, so the third step says write a KCL expression for each node from part 1. Again, there's only one node that we're interested in, and that's Vx. And so let's go ahead and write that expression. That's going to say from KCL, that's going to be that I1 plus I2, right? The sum of my currents entering the node is equal to the sum of my currents leaving the node. Well, the only current leaving the node is I3. Okay? And so that's 3. We're done with part 1. We're done with part 2. Done with part 3. And so part 4 says use Ohm's law. Okay, we know Ohm's law, right? to substitute voltages and resistances into the expression or expressions from part 3. So this is my expression from part 3. And what does it mean by use Ohm's law to substitute voltages and resistances? Well, I know that I is equal to V over R if I rearrange Ohm's law. And so basically what step 4 is saying is I can take all of these currents and I can represent them in terms of the voltages and the resistances across the resistors where I define my currents, okay? So for I1, I can rewrite I1 is equal to the voltage across this resistor, which would be 1 volt minus Vx, right, the difference, divided by 1K. And for I2, I could write this current as 2 volts minus, so this would be I2, 2 volts minus Vx divided by 5K, right? And then for I3, I could write that current as Vx minus 0 volts, right? I'm going across the resistor this way, divided by 3K. Okay, so now I have expressions in terms of V and R for all of my currents, and I can substitute those into this expression, or this equation. So that would be step 4, and I'd be done. And my last step here, basically to complete this problem, tells me that I just need to solve the resulting system of equations. Well, in this case, we would only have one equation. There's no system because there was only one node that we were interested in, right? But in a case where you use nodal analysis to solve a circuit that has multiple unknowns, you would have a system of equations with several unknown voltages, and you would just go ahead and solve that system to obtain the unknown node voltages, okay? In this case, like I said, there's only one equation that we're solving here. It would every single equation would be, or every single term in that equation would be in terms of Vx, so you can simply rearrange, solve for Vx, and then this problem would be done. Okay, so that's a brief overview of the general process, and now I'm actually going to go ahead and make a circuit, and I'll solve it using nodal analysis. I basically did that in this one, but might as well just go through the whole process again and solve the circuit this time. In the next video, that's exactly what I'm going to do.